senses. Okay, and then what we call the principle of faunal succession. And what the principle of faunal succession basically says is it was the precursor to the idea that would lead to evolution and stuff like that. And what it basically says is that as we look at the rock column, you can correlate the age of the rock, which means you can kind of relatively date the age of the rock based on the complexity of life. As we go further and further and further back, life will get simpler. Okay, the complexities of life will get less and less and less within reason. Obviously, there were very complicated species millions of years ago that no longer exist. But what it basically says is that you will find the ancestors of creatures before you find the current day creatures. Okay, and so if you find a rock that contains a dinosaur and a rock that contains a woolly mammoth, and we now know that woolly mammoths obviously evolved much later. You could say that the rock that has the woolly mammoth in it, the tusk from the woolly mammoth, is much younger than the rock that has the velociraptor claw in it, for example. And you can do this comparing rocks that are on different continents. You can compare, if you find this fossil in India and you find the same fossil in Oklahoma, well, you could say that those two rock layers, although they are dramatically different rocks, are from roughly the same period of time. Now that leads us into a very important concept, which is called index fossils. Okay, and index fossils are the remains. Now we talked about fossils before, but you've done it in school before. Fossils are the remains or impressions of life, okay, preserved naturally in rock. Okay, now the most typical ones you will think of are things like dinosaur bones, but you also have impressions. You could have leaf impressions, footprints. Okay, there are things called chemical fossils, but basically you're talking about the remains of extinct creatures preserved in rock. Now, index fossils are really important. What they basically are, they're like bookmarks. Okay, they are the remains of creatures that we know lived during a very limited period of time. Okay, and have since gone extinct. So when we find those fossils, we can say, oh, this rock is roughly from this period of time. Now, it's not an exact thing, but it does give us a general idea. And index fossils can be really useful for identifying specific periods of time. So for example, you've got these things. These are called brachiopods. Okay, brachiopods were present during a specific period of time. You've got trilobites, which is what we just saw before, which were also only around for a specific period of time. Okay, and then you've got ammonites, like this one, which were around during the last periods of the dinosaurs. And so when you find these different fossils, you're actually capable of saying, hey, that rock is probably from this time or that time or another time. Now, if we're looking at index fossils, you can actually see in your reference table in that center column that we haven't talked about, we will be talking about this for the next few days, so make sure you take it out. If you look down here, you will see all of these lettered creatures. These are all index fossils, and you can actually see right here all those different letters that apply to these guys. Now, if it's a little difficult to see, it's okay. I got you. Ready? Boom. Ooh, color, much better, a little clearer. But I got you even better than that. Boom, boom, boom. Mr. G's awesome. Okay? These are all your index fossils. Now, these are creatures, okay, that existed during a specific period of time. And when we find these, they allow us to identify the period of time that we're looking at. And so when you find something like a Coelophysis lived during the late Triassic period. Okay, now when the heck was the late Triassic period? Well, if we look, okay, we have the Triassic period right here. Okay, so Coelophysis, boom, right there. Okay, Coelophysis existed during that time frame. So if you find a rock with a Coelophysis fossil, you know you're talking around the late Triassic. When was the late Triassic? You can see right there. Okay, the late Triassic. Okay, you're talking probably around 240 million years ago, give or take. 200, somewhere in that range. Okay, 210 million years ago. You're talking a very short range of time. But that gives you an idea of when Coelophysis would have been around. And the same goes for any of these particular fossils. Okay, so index fossils are incredibly useful for us. Okay, so if we look here, we have a picture. Okay, and I'll leave it on screen for you guys for a couple seconds. I'd advise you pause it right now after I finish asking my question. And I want you to look at this picture and I want you to tell me, okay, which one is the oldest and why. How do we do it? What's the principle that we would use? Okay, so pause it. All right, so if we're looking at it here, okay, the youngest, well, that one's really easy to tell. We have our glacial debris. Why? It's all the way at the top. Okay, so we have to assume that all of this was originally horizontal, right? Now, what we've got a couple things here. We've got a break here. So what's that called? That would be a fault. Okay, over here, we've got a dike. Over here, we've got another dike. And over here, we have a sill. Here, we've got a batholith. See how this whole layer is twisted? So what we got to do with that one? We're going to have to go and twist it and make it nice and stacked. So if we were looking, we could easily say, okay, youngest, and then this layer would have come. Now, this green layer. Okay, we would say it's the next one in line, but see how you have the dike here? What does that tell you? This dike is cutting through this green layer. So that green layer had to be there at the time. So it would actually be this, then this igneous dike here, right? Cutting through, okay? Then the green layer, then the conglomerate, okay? Then the fault would have happened. Why? Because the fault breaks this guy apart. So in order for him to break apart, this layer had to be there. Then the sandstone, okay? And work your way down, okay? You would then have dike A would have come through, okay? Because it cuts through the shale, okay? Then you'd have the shale layer. Then you would have the limestone or dolostone layer here, okay? Then the batholith would have come in to play. And then the siltstone, and finally the white sandstone down at the bottom would be your oldest layer. So all the things we've been talking about involve this geologic column, this idea that scientists have constructed that if you take all the rocks around the earth, you could effectively create this one column that would have rocks from every age throughout the entire 4.6 billion year history of the earth. Now remember, this is a concept. This is a concept that scientists have come up with. Nowhere on the earth does the geologic column exist like this because there are forces at play. Weathering, erosion, deposition. These things have been at play since the beginning and they are still at play now. So nowhere on the earth will you find all 4.6 billion years. But there are places on the earth where you can find a lot of the earth's history there. But sometimes you actually end up with gaps in that geologic column in a particular location. And they're more than just like, oh, well, something happened, like huge gaps. These gaps are referred to as uncomformities. Unconformities, the geologic definition is breaks in the geologic record caused by uneven erosion and weathering at the Earth's surface or of the Earth's surface. So what does this mean? This means that at one point you had the rocks there, but those rocks got eroded and weathered away, and they are no longer there. And so you have this huge gap. Now, these things happen all over the place. One of the most famous places this happens is in the Grand Canyon. So if you're looking at the picture in front of you, this is actually of the Grand Canyon. So here we have the different layers from different time periods. And here we have what we call the Great Unconformity. And Great Unconformity is this huge gap in the rock layer that exists. The rocks down here come from about 1.5 billion years ago. And then this layer, okay, comes from about 550 million years ago. So you go from 1.5 to 550 million, billion. So you're missing almost a billion years of history. So if we look here, right, these are the different rock formations that you have in the Grand Canyon, okay? And the Great Unconformity, once again, is right here. It's this gap between the red and the green right here, okay? And so you have this huge gap that exists between there. A billion years of history just poof, gone. Now, how did it go? Well, scientists have lots of different ideas. We think that during this time, there may have been an ocean that was there, and so the rocks that were laid down there were sedimentary rocks that were easily weathered, and then when uplift happened later on, those layers easily got broken up. There may have been plate tectonics that caused extra erosion or things like that. There's a lot of different ideas as to where that comes from. I will see if I can link something down below where they have some information as to why this may have happened. But they do happen. Now, it's not just here, okay? Unconformities happen all over the planet. There are lots of different types of them, okay? Sometimes they can happen like this, where you have, see this layer here, and then there's an there's another layer here. Well, there's a gap, a break in the rock record there, okay? Sometimes you can get stuff like this, okay? Where this white line here, superimposed obviously, was is an unconformity. There were rock layers there and they got eaten away, and then new deposition happened and got rid of those rocks there. Now, how does it happen? Well, it's relatively simple. So you start off with your basic rock layers getting deposited, A, B, C, D, okay? And plate tectonics is gonna happen, and so what happens? The layers get bent and twisted up like this, okay? And they get pointed up like that, okay? And when that happens, what's gonna happen? Well, you're gonna get erosion. And so you see everything on except for A must have been a hardy stone or something like that, a very durable material. Differential weathering happens, right? And you see how layer D, which was originally here, all that got rid of, all C got rid of, B except for this little bit here. And then what happened? You got more deposition on top of it. And so all the rock that used to be here now got eaten away. Now this is a small snippet, but imagine this was many square miles, big huge distance, a big canyon. Okay, sometimes you can have this process where once again you have your layers deposited and you get uplift and tilting and erosion, and you see how layer C has gotten almost chopped down to nothing. Now had this been exposed for even longer, you might have completely gotten rid of layer C and then eventually deposited layers F and G on top of it, and you have what we call an angular unconformity. So unconformities happen all the time. And that's why we can't just study one particular place on the earth and say, okay, there's all over its history. We need to look at everything. But I hope this helps you to understand how relative dating happens. And when you see something like this, these gaps, I hope that helps you understand why we also need to do the numerical dating, which is just...
Alright guys, so that does it for our relative dating video. Please make sure you've taken notes. This stuff is very important. Please make sure you do the homework assignment that is attached to this. And I will see you guys later. Hope everybody's safe and happy. Alright guys, bye.